5 physics questions. Question 1. Artificial gravity based on centrifugal force. Will it stop working if you jumped off the ground? If you don't know what artificial gravity is, here is an animation. Here are some objects in no gravity in some kind of a donut. Because the donut is spinning, the objects will randomly collide with each other but finally end in a stable position, pushed up into the wall by the centrifugal force. But will it work if you jump inside it? Question 2. Water and air is transparent, at least somewhat. So how come we are able to see air bubbles underwater? Question 3. We know that high energy electromagnetic waves has a big frequency. We know gamma rays and X-rays has such a big frequency it can ionize your body cells and cause cancer. We know that from this equation. From this equation we can see the energy of a photon is given by Planck's constant times the frequency of the light. It turns out that visible light, visible electromagnetic wave, has a higher frequency than microwaves. So they have more energy. So shouldn't it be safe to put your hands inside the microwave, but instead dangerous to put your hands in visible light? Question 4. When spaceships are re-entering Earth, they heat up quite a bit when they fly through the atmosphere, and they need some kind of protection, as you can see in this animation by NASA.
Oh, that's hot. That's hot.
So how come we don't need any protection when we exit the Earth's atmosphere? You can see there's no black heat shield here. Question 5. I don't know if you noticed, but don't go and test it. When you use the oven and use aluminium foil, it is possible to touch the aluminium foil right after cooking, almost. But you can't touch anything else. You will get burned very badly. So how come it's possible to touch the aluminium foil, but nothing else? While you wonder about these questions, and before I answer them, let me talk about the sponsor Brilliant. I contacted Brilliant myself because we have a lot in common. We try to explain science intuitively with nice and clear visuals. But Brilliant takes another approach than just videos. They have fascinating, challenging problems with interactive graphics that helps you understand the material. And if you didn't get it the first time, every problem comes with an explanation that breaks down the problem into smaller parts. What I really love about Brilliant is the nice app. You can sit and relax and learn something. Or pull out the app if you have a minute or two. You can sign up for free and get access to free daily problems and the first chapter in all of the courses. If you want more, you can use this link to get 20% off brilliant.org/hexenophysics. It will give you access to all the courses and all the archived daily problems. The link is in the description as well. Alright, did you think about the questions? Because now I'll go through the answers. Let's start by question 1. Does artificial gravity stop working if you jump? Well, it's tricky because it seems like if you're jumping, you're no longer being accelerated around the ring. But I created this jumper so I can simulate and show you why the gravity still would work. I showed you this simulation of an artificial gravity device before. I'll use it again but replace the objects with the jumper. So here we are, and when it jumps, you can see that it clearly works. Why is that? Well, because when you jump, you still have some rotation of inertia. The exact same situation if you're traveling straight. If you jump, you will not lose your energy. In this situation, translational, not rotational inertia though. And so you land the exact same place, at least if we assume there's no air resistance.
Now, reality can be whatever I want.
As I think you already have experienced, if you jump on a rotating planet, you won't lose your rotational inertia, you would follow the planet. So it would still work, but there's other problems. It actually happened in my simulation. When the jumper jumps, it looks like it's falling over. That's because in the air it's not being accelerated and therefore it's flying straight. When an object is flying straight, inside the circle it looks like it's falling over. That's because the lower part is rotating faster than the upper part. It's happening on the Earth too, as you can see in this animation. It's called the Coriolis effect. But it's not as noticeable because the Earth is too big. However, the fake gravity wheel will probably not be as big. So while you can jump, you'll probably fall over. Perfect, now let's answer question 2. Why can you see air bubbles underwater? Both materials are transparent, however they have a different index of refraction. Index of refraction is a number that tells how fast light can move inside a material. It turns out that light can move way faster in air than in water. That will cause the light to bend and change direction. I can show you easily in this animation why. Imagine the cylinder is light, moving really easily on the concrete, just as light travels easily in air. Now one side of the cylinder meets a material where it has to travel slower, that's why it's turning into the material, as you can see. So the animation was supposed to show this. Light comes from one material, hits another material that it has to travel slower in, and therefore it changes direction. Here is some water, and here is a bubble that has the same index of refraction as water. When I put it in, you can't see it because it has the same index of refraction. Completely invisible, because the light does not change direction, so you can't see it. Here's another ball. It has a different index of refraction than water, so now I put it in, and you can easily see it. This is the exact same situation as with air in water. Because the index of refraction is different, it will cause the air to change direction, and therefore you can see the object. This explanation was a bit quick. I have 2 videos about light and refraction if you want to learn more about it. Question 3. Why is visible light not dangerous when microwave waves are? My friend Zapp from the YouTube channel Zapp Physics will help me answer the question.
Thanks for having me. As it turns out, the answer to this question has to do with energy density. Although it is true that microwaves are less energetic than visible light per photon, a typical light bulb outputs around 50 watts of power, whereas a microwave operates at about 1,000 watts. What's more is that all of the energy from the light bulb is spread out in the roughly 50 cubic meter room, but all of the microwave's power is put into a volume of about 20,000 cubic centimeters. A quick back-of-the-envelope calculation tells us that the energy density in the microwave is about 50,000 times that of the light bulb just sitting in a room. If you filled your living room with 50,000 light bulbs, you would probably start to see some negative effects on your health. Anyone who's focused sunlight down to a point with a magnifying glass knows just how dangerous visible light can be at high energy densities. Over the surface of a typical magnifying glass, the sun outputs a power comparable to that of the light bulb in a very similar frequency range. But when the magnifying glass focuses all of that light down to a tiny volume, the energy densities get huge and can easily cause some damage.
Thank you, Zapp. Zapp Physics has a lot of interesting physics videos, and I recommend watching them. Link is in the description. Question 4. Why do spaceships heat up when entering Earth, but not when exiting? When the rocket is launched, it starts from 0 velocity, and it flies faster and faster, but in lower and lower air density. This creates very little aerodynamic drag and therefore very little heat. The air resistance and therefore the heat generated, it depends on the density, rho, and the speed of the object u, and the area of the object a, and then a constant depending on the fluid c. When re-entering Earth, the spaceship is flying extremely fast. We are talking in the scale of kilometers per second. The rocket can't brake before there is relatively dense air, so it will be braked in dense air at tremendous speed. And all the kinetic energy is being converted into heat. And there's a lot of it. Question 5. Why can I touch aluminium foil in the oven and not get burned? The reason you won't get burned is 2 things. Firstly, there's very little aluminium and therefore very little material to hold the thermal energy. It's the exact same situation as with sparks from a grinder. You are getting hit with molten iron, but there's so little it's not dangerous. So if you took out a hot bar of aluminium from the oven, you would definitely get burned. Next, aluminium is a material with a very low heat capacity. Heat capacity is a measure of how much energy it takes to heat up a material. So at a given temperature, aluminium does not have a lot of energy to give, but with water it's different. As you know, it's way harder to heat up, but once it's heated, it has a lot of energy, so it can burn you easily. If you want to help me create more physics videos like these, become a patron, subscribe to the newsletter, or subscribe to the YouTube channel. The links are again in the description. Thank you for watching.
What I want to know is what's going on between these two bits of metal.
Magnets repel each other.
Well, then what does that mean, or why are they doing that?
何？お前はもう死んでいる。